It's here, the biggest investment I have made this year. An actual microphone, unlike whatever this is. Alright, my name is Zakaria, I'm a mechanical engineering graduate, and these are a few things you should know before graduating as a mechanical engineer. Computer-aided engineering is my favorite part of mechanical engineering, even though everybody loves math. I mean, who doesn't love solving integration problems and complex algebra? This field can be subdivided into CAD, computer-aided design, CAM, computer-aided manufacturing, FEA, finite element analysis, stress analysis, CFD, computational fluid dynamics, and many more fields. In my opinion, you should have at least a minor experience in each and every one of these, and then pick one of them to explore further in an internship or a project. This will allow you to have some experience to bring to your first job and start your career beautifully. The first one students get exposed to is CAD, computer-aided design. In short terms, it's 3D modeling, but that term could be conflicted with 3D modeling for video games, for architecture, for decoration, and many other fields. You can start by learning the basic tools in order to recreate something you could imagine, but then I would advise you to eventually get into design for manufacturing. It is designing a part while thinking of the way it's going to be manufactured. For example, when extruding a part, you're going to be thinking that it's going to be CNC machined, and when doing a revolved boss, you would think that it's going to be made on a lathe machine. Some people focus on getting as many certifications as they can in many different softwares and then try to use that to get their first job, but at the end of the day you should stick to one, learn it very well, understand the principle behind creating the 3D shape you imagine, and then you could move on and jump from any software to another. As my professor once told me, you should never let the software be the obstacle. As an engineer, you should be able to use any CAD software intended for engineering and take a day to learn where the different buttons are, and then you should be able to use it professionally. Another aspect of computer-aided design would be assemblies and motion studies. In the end, I want to emphasize that this skill is really important in your training as a mechanical engineer, and you could, for example, take part in local CAD competitions like I did in my second year of mechanical engineering. I competed in more than 3 of these competitions with my team and won 2 first places and 1 second place. To give you an idea about these events, this was the topic of one of the competitions. We had 12 hours to design and assemble a machine that would roll cables with different lengths and then zip tie them in 2 different positions before defending this idea before a jury and explaining how each part worked in a 5-minute presentation, which is really tight on time. Computer-aided manufacturing is the cousin of CAD, and it aims to define the process of obtaining the designed part in CAD from raw materials. After choosing the right CNC or machining center, you divide the process into different steps of material removal, drilling, milling, etc. All of this while controlling cutting speed, tool trajectories, specifying roughing and finishing passes to ensure maximal quality. To be honest, I didn't dive deep enough into CAM to talk about it in more detail, but I do have a minimal experience and a basic understanding of it. FEA, or finite element analysis. I really do like this subject, and I'm going to explain it the way my professor did in one dimension. I could never do better. Suppose this is the real solution for a complex problem where conditions are applied on both ends for simplicity. Well, one way to numerically solve this problem is to decompose the domain into small segments and solve for each small segment by itself. We call this discretization. Bring the problem to a 2D, then a 3D, and you basically can solve the most complex physics problem given enough computational resources and the correct model. Choosing the correct model is really important, as it means choosing the right equations to solve, and this would drastically change the correlation between the numerical results you got and the real-life experiment you could do in a lab, for example. What you see here is what we call meshing, and generating a good quality mesh is critical in order to reduce numerical error and eventually reach numerical stability. My professor used to say, a good mesh is a beautiful mesh. Now, even if this first mesh is finer, the second one is more structured and wastes less processing time for the same or even better results. We use FEA for many types of simulations, and this is the first type of them. Stress analysis is one of the most practical applications of FEA. Here we are checking if our mechanical design survives the loads we are going to apply in real life, by applying forces, constraints, temperatures, pressures, etc. Then the solvers gives us stress, strains, safety factors, and even deformation. The key to do a correct simulation is to understand the physics behind it and the behavior of the material you're choosing. You need to pick the right material model, boundary conditions, and load cases. If you select a wrong part, for example, by mistake, you could get completely different results and a completely wrong stress distribution which is not physical or does not reflect the reality of your system. In one of my projects, I used stress analysis to do what we call a geometry optimization. We had the freedom to choose any type of mechanical part we wanted to do, so with my partner we chose to do a bicycle. Basically, we took a first initial shapes, we made some hypotheses about the distribution of forces a biker would apply on the structure of a bike, we took a 2D problem to simplify it, and then after getting the results of the stress distribution, we told the software to start by removing some material from the parts and then cycle in order to reach an objective function. Our function was to minimize the strain energy that would result in displacements and deformations. Here we told it to reach at least 50% of the initial volume, since the initial volume is a huge plate. This result would be completely different if we had chosen a different type of configuration or a different type of loads on the bike. And this shows how sensitive the outputs are compared to your inputs. This is why you should be really careful in choosing the right conditions. The last subject in this video would be CFD. It is the subject I personally have the most experience in, since I did a 2-month summer internship and my end of studies internship by using CFD tools. Computational fluid dynamics is numerically trying to solve the equations that describe the motion of fluids. These equations are really complex and require a good computational power in order to obtain significant results. Just like stress analysis, you need to define the correct boundary conditions, but also choose the right turbulence model. And of course, to obtain correct results, you need to understand what you're doing and understand what type of equations you're solving and what type of flow it is, if it's laminar, turbulent, and even in the turbulent there are different models to choose from. When you obtain your results, they are not directly available, which means you need to do what we call post-processing, which is the part where we calculate the resulting forces or the pressure applied on a surface, for example, to describe the interaction between a fluid and a structure. If we take the wing of a plane as an example, we can calculate the pressure above and below the wing and then determine the lift force and the drag force. Many things could go wrong in your simulations, starting from the bad quality of the mesh and ending by a wrong decimal point, which completely destroys your results and gives you unrealistic behavior of the fluid. In the end of the day, this is just a brief introduction to mechanical engineering. If you're thinking about choosing this field in your studies, I really advise you to, but it's really for people who love this field and want to work in the automotive industry, in the aerospace industry, in the marine field, in the industrial field. You have so many different fields to choose from later on, and this is a really good advantage of mechanical engineering. In the end, I want you to remember that mastering the fundamentals is what makes you a powerful engineer. That's it for today. I hope you enjoyed this video. If you would like to see more engineering content, don't forget to subscribe to my channel and see you soon.